Hello, everyone. I'm Zhen Tai, and my partner is Yang Gao. Today, we are going to present a paper, Interpretable Explanation of Black Boxes by Meaning for Perturbation. Here are the content of our presentation. First, I will talk about what does this paper do. Then I will introduce a brief introduce about the proposed method and the contribution of proposed method, same as the principle. And then my partner will give an introduction about the experiment, results, and the conclusion, for and against. Then finally, we are open for the question. First, the application of machine learning algorithm image saliency method are used to summarize the attention map of neural network in an image. However, these methods are limited by their heuristic properties and architectural constraints. This paper presents a general framework for learning different interpretation of any black box algorithm, and they also propose a framework to find the most relevant part in the image and the classifier decision. Different from previous work, their method is model agnostic and testable because it's based on explicit and interpretable image perturbation. The existing problem of interpretation for black box predictor is that intuitive visualization method is only heuristic and the meaning is unclear. Black box predictors such as deep neural network are powerful but opaque. People are interested in explaining and understanding them after learned by DNN. This is still an unresolved issue. One reason is that we lack a standard interpretation for classifier. Black box function already learn from data automatically, and we want to know about this function. This paper developed a principle and method to explain any black box function by determining mapping attributes, and the internal mechanism is used to implement this attribute. We focus on the mapping attribute because it can give us a rule that describing the relation between input and output by function. Another method is that this paper proposed a general explanation framework, Meta-predictor, and identified that neural network artifacts are the main attraction of interpretation. The definition of artifacts is that the pixel showed in the scanned image but does not exist on the object. The third contribution is reinterpreting network saliency in their framework. These provide a neutral general based on gradient saliency method, which backpropagates in several rounds to learn an explanation by integrating information. They also compare the meaning from this technique with other methods. Their work is gradient-based method, which backpropagates the gradient of class label to image layer. Other backpropagate methods, including DeConvNet and guided backprop. Another technique is to bring network activation into visualization. Class active map, which can explain CNN model and return a class activation map, like a heat map. Let me briefly introduce the class active mapping. Here are two parts of CAM. Feature extractor and feature classifier. The feature extractor is produced by global average pooling, GAP, and the output is the feature map. The feature classifier is a fully connected layer and the output is a salience map. The problem is that CAM can only explain why CNN is so classified, but it cannot explain why CNN can locate the area well related to the label. Here is the comparison between proposed method and related work. CAM methods are not model agnostic and limited by neural network. It is necessary to modify the network structure or access the intermediate layer to get the visual result. The problem of adding a mask to the part of image would change the classification result. and would be limited by its target region and its similar region. While proposed method in this paper can differentiate and consider the connection between different image areas. Local explanation paradigm and the saliency method proposed in this paper are related to the line framework because both methods use information about the input x0 and the output is from the label of x0. X0 is generated by perturbation. However, NIM needs 5,000 iterations to converge to get a heat map, and the method in this paper only needs 300 iterations. Here is the comparison with other saliency methods. Column 1 is the ground truth, and column 2 is proposed method. The rest of column is the other salience method. By judging from the position of anchor and the edge of the heat map, it's obvious that the proposed method has the best performance. The black box is a mapping function f, which maps the input space x to the output space y. The mapping is usually done in an opaque learning process. The input image x, lambda is a pixel value which represents as height times width, and the lambda is a discrete domain. And output is a Boolean value, -1 and +1. Take a Robin, for example, -1 means not in the class, and +1 means in the class. Suppose that the following rules are used to explain a Robin classifier. XC is one Robin image as input, which is the subset of all Robin image X. Since black box function f is imperfect, such rules apply only approximately. In this case, this paper used expected prediction error to measure the realistic explanation, which represents as this equation, while delta q is the indicator function of event q. Notice that L1 is expected prediction error of the classifier. Q1 requires the image x on the distribution of black box function f. Q1 is not very insightful, but it's interpretable, since XC can be interpreted. The advantages of explanations as a meta-predictor are that the faithfulness of image can be measured as prediction accuracy. The machine learning algorithm can select the most suitable Q from large number of Q and apply the optimal Q to specific function f, so as to automatically discover the explanation. Find the most suitable Q is similar to traditional learning problem which can be implemented by the formula of regularized empirical risk minimization. Here are two purposes of R of Q. First, to generalize the explanation Q in n sample, and pick the explanation Q which is simple and interpretable by optimization. It is usually not enough to find a good explanation to meet the requirement of simplicity and explicable. So a good explanation must combine with the information to make people believe. Therefore, here is the upgraded version of Q rule, where the theta and where the x and the theta x means that x and x prime are related to the angles, rotation angle theta. The interpretation of large angle can usually be applied to the interpretation of small angle, which make the theta equal to 0. Therefore, the maximum angle means that find the maximum information as possible. Local interpolation refers that rule Q predict the black box function f at x0 and the response of x0's neighbor. If f is smooth at x0, then we can construct our Q rule by first-order Taylor expansion. The gradient of f of x0 as an indication of salience map S1 x0. The large value of gradient affect the network output, so make the second equation does not suitable for linear classification model, because f of x is independent with x0, which cannot to explain the linear model. Furthermore, This formula studied the change of black box function from x0 to any displacement x minus 0. For linear classifier, regardless the starting point x0, the change are the same. This can explain why there's no obvious obvious information in the image, but the saliency is still so strong. For saliency, the interesting point is to find the area that affect the output of black box function f. Therefore, consider deleting parts of image x0 by adding perturbation to the image to whole image x. We can use x0 dot product mask m, which is equivalent to this dot product function in the form of Taylor expansion. For linear classifier f, the saliency is weight dot product the deleting part of image x0. For large resolution image, the saliency is large, and the problem will be solved in the next section. The reason why we're interested in saliency is that saliency map can recognize the area that generating output x0 from image x0 in black box, and we can observing the change of value f of x and deleting different area r. For example, f x0 equal to positive 1 means a Robin image. We hope that fx also equal to positive 1 if the given image is the perturbation of x0, and we hope this explanation can explain the relation between f and x0. The reason of deleting information is to simulate the nature image, resulting a more meaningful explanation for perturbations. Deleting information we specify as a region R. Using a constant value to replace region R and adding noise to blur the image. For this formula, M is the mask which between 0 and 1 to each pixel value U to determine the micro-perturbation. U is the average color, eta U is Gaussian's loss sample for each pixel, and the sigma 0 is the maximum isotropic standard deviation of the Gaussian blur color kernel. And here is the output from this micro-perturbation. Take the constant scenario, for example. If this mask equal to 1, then 1 minus 1, this part becomes to 0, and the remaining part is the salience map, which is in blue region. And if the mask is 0, then the first term becomes to 0, and the remaining is average color mu 0. Then the mu 0 is in the yellow part. To sum up, given an image x0, the purpose is to delete some area from image and observe the change to explain the black box. What we need to do is find the area with the largest amount of information, then delete it. So which part should be deleted and which part should be preserved? For deletion, black box function f of x generates many score factors about image content and find the smallest deletion mask m to increase the difference between these two functions in score. The left side is the output from micro-perturbation, and the right side is the normal salience map, and it presents as in this equation. Preserve is the reverse of deletion only when the micro-perturbation is greater or equal to salience map, and it presents as this equation. Notice that the lambda in here and here is the constant value 10 to the negative 4. Another difference is that the deletion method deletes as many information which can stop recognized as possible, while the preservation method finds the smallest image subset that can make classification reach a fixed score. Here are two ideas to reduce the artifacts. For deletion method, do random learning instead of depending on the detail of single mask M. Total variation TV norm and upsampling it from a low resolution version. And this equation is formed based on these two ideas.
Okay, Jingkai, let me control your screen.
Yeah.
Okay. Hello, everyone. I'm Yang. I'm here to explain this the experiment in this paper. So for experiment, there are 6 sections: interpretability, deletion region representativeness, and minimality of deletions, testing hypotheses, animal part saliency, adversarial defense, and the final part is localization and pointing. So for the first experiment, interpretability, so let's first see the bottom row. The leftmost is a pickup, and the second mask is the proposed method generated mask. We can see this mask not fully occupied the red bounding box. So let's jump to this contrast excitation. This is another method proposed as saliency map. We can see that it focuses on the bumper. So we can test it if which one is more explainable. So firstly, we test this mask to blur this. What we expect it should be the confidence of this should be decreased very fast, and it is. It decreased from 71% to 1.8%. And let's see another method. They blur this bumper. We expect it will decrease some confidence, but actually increase this confidence from 71% to 85%. So this experiment can prove that the proposed mask truly explain where does this neural network focus, where does it look at. It's not as human thinking. This is a pickup, so we focus on the whole pickup, but actually they are finding the more individual region. So let's go to the second group of this experiment. So in order to identify what is where is the chocolate sauce, as we human see this cup of chocolate sauce is that, but actually according to this proposed method, they are focusing on this spoon. You can see here. They are focusing on this spoon, and we can do 2 experiments to test it. If we blur this cup of chocolate sauce, yes, the confidence decreased, but not very much. It decreased like from 61 to 35. And if we blur the spoon, which is not chocolate sauce at all, it decreased from 61 to 1.5%. This is looks weird, but the explanation from authors is that this chocolate sauce can appear in other category, like I don't know exactly, but we can think about that maybe like coffee or some breakfast or something. But this spoon is individual in chocolate sauce. So the neural network is not really look what it is in like intuitively, but they are looking for the individual or more specific for this category. So for the second experiment, they are going to find the purpose of this proposed method is to find the smallest region, to find the most efficient way to find the object. Like here, there in the middle of the image, there's a bird. So if we this is a mask they generate. So if we set a threshold, like threshold as alpha equal to 0.2, and we said that all these purple region set it to be 0, and the yellow region as 1. So we can think about that. Let's just delete this bird region, and the confidence of this this is normalized softmax. The confidence of this from 0 to 0.2 decrease very fast. That means this region contain the a lot of the major information. So if we expand this alpha from 0.2 to 0.4, they increase annulus region. This annulus region was deleted, and which lead to very small decrease from 0.2 to 0.4. So which means their proposed method is high efficient, contain the most I can say major informations. So the third experiment is about the almost the same as the previous, but they are doing the suppression experiment. So in order to achieve the like for example the first group, the leftmost group bar, to in order to achieve suppressive effect as 80%, how much pixel we need to blur. So comparing with other method, this blue bar, which is proposed mask, blur the minimum number of pixels, which also means this is the most efficient. They contain the most information uh, than other method. So that's the third experiment. So the fourth experiment is a little bit interesting. During other experiment, the author noticed that uh, this mask prefer focus on the eyes of the animal instead of epidages like feet. So they put the mask on the image, and they really find that this saliency map is overlapped with this red dot. Red dot is the eye, and the green dot is the feet. And this red dot and the green dot are from this annotated images, and this is the reference at least here. And for the which is this is fifth experiment. Um, so here on the left, this is a comparison between proposed mask in the middle, based on the adversarial example, and adversarial mask in the bottom, based on the nature images. As we see what we see in the previous class, the adversarial example, perturbation was generated with whole images. It will add epsilon or some I can say perturbation to the every pixels. So without any differences. But in this method, they just identify this instrument, and okay, this is still on this. This is attacked image, which identified as padlock here, adversarial example, but it still can identify this is instrument. So on the right, this graph, this is the accuracy of binary classifier. This classifier is going to classify this image is clean or adversarial. If this is yes, and behind this, in this experiment, the author doesn't show the result. The also test that find that this proposed mask can recover the image from adversarial examples. In other words, minimize the adversarial label, but improve the original label back to the top predicted class. And as they know, this is the first work that is able to recover originally predicted labels without any modification to training setup and the network architecture. So the last experiment, this is not like the previous experiment. They are going to show they are the state of the art, but here, because their target is now to find the most accurate localization and pointing, so we can see they cannot beat other method, like in this matrix, the contract excitation backprop is the best. Beat this proposed beat this proposed method. So they just do this experiment, and but not to say they are the best in this field. So all in all, in this paper, they proposed a framework based on this paper to learn the explanation as meta-predictors, and they present a novel image saliency paradigm that learns where an algorithm looks. And unlike many saliency techniques, the proposed method explicitly added to the image, making it interpretable and testable. And the author also shows numerous applications of this method and gave a new insight into the fragility of neural networks and their susceptibility to artifacts. So for this paper, the strong point is using a perturbation to interpret the classified image, and the proposed method to find the minimal they proposed a method to find the minimal image parts, which has most information, and try to delete it. And the third part, the third point, they proposed a comprehensive experiment, fully proved that proposed method is the state of the art. And the experiment shows that where the algorithm looks, I think that's a brilliant and a very intuitive way. And for the weak point in this paper, I think they don't show the recurring effect from adversarial examples. So any questions? Thank you.